In Lesson 5.5, Bases Other Than E and Applications, we're going to take a look at what happens when we have exponential functions with bases that are not E. We're very used to these, perhaps 2 to the x power or 7 to the x squared power, things like this, where the bases are not necessarily E. We're going to talk about how to differentiate and how to integrate functions of that type, as well as how to differentiate standard logarithm functions, such as the logarithm base 10 of x. You'll see that it involves a little bit of a formula, but really no big deal as long as we follow the procedure throughout. So we'll take a look at all that. We'll also look at another definition of E. Since we're now moving away from E, we may as well go back and look at what E actually means in another way. And then we'll finish this lesson up with one more slope field and differential equation problem. So all this being said, why don't we focus on the basics in our first two examples, simply solving for exponents or logarithms. Let's go ahead and take a look now. So our first example, example A, will harken us back to the days of Algebra 2, when we first learned about how to deal with exponents and how to solve for them and all that good stuff. Hopefully you recall from Algebra 2 that the way to deal with exponents is to apply a logarithm to them, because one of the properties of logarithms is that they bring exponents down and turn them into essentially a coefficient. So let's see how this problem would work. Of course, before I do anything else, I do need to get the exponential part of this equation by itself. And so I will simply divide both sides by 3 as such. Now I'm at the stage where I want to bring this exponent down. And the way I do that, as I said, is with a logarithm. Now, just for the sake of simplicity, I'm going to use a natural logarithm, although quite honestly, any logarithm should work for you. So now that I've done that, our exponent will come down and turn into a coefficient, and we'll end up with an equation that looks pretty much like this. No problem there, and you can see that what I'm trying to solve for, this x right here, this term is being multiplied by the natural log of 5. And so at this stage, all I need to do is divide by that natural log of 5. And what we'll end up with is this right here. Of course, finally, to get x by itself, I simply need to add 1 to both sides. So if I add 1 over here, I get that. And if I add 1 over here, well, now x is by itself, which is exactly what I wanted. So, how do I go about evaluating this nonsense here? Well, this cannot be done by hand. So at this point, you really do need to pick up your calculator and just feed this mess through. Be very, very careful when you're feeding this through your calculator. We need to have parentheses almost everywhere. There are parentheses around the argument of the natural log. There are parentheses around the numerator of the fraction. Really, I should have parentheses around the denominator of the fraction as well. And so I can evaluate that and then add 1 to it. If I do that, what I should end up with is simply 3.085. And that is our final answer. In fact, if you take this number here and store it as x, remember how to do that in the TI 83 and 84. You simply hit that store button, which says STO. That's right above the on button. That'll bring up an arrow on the screen. And so what it will say is the answer arrow, and then you simply need to hit the X button, which might say xt or something like this, maybe x theta. And so we store that value as x. Then all you really need to do is type back in the left side of this equation and see if you don't get 86 as your result, proving that x really does equal 3.085. So now that we've done this example dealing with how to mess around with the exponent, let's take a look at one more Algebra 2-ish example where we're going to solve for the argument of a logarithm. After that, we'll move into some calculus, and it will be good. But let's go ahead and take a look at B first, just to solidify our previous knowledge. So the fun part about example B is that we can actually solve it a number of different ways. I'm going to present to you 2 of those ways and invite you to look for other correct ways as well. But as you see, we have a log base 5 of this nasty argument, the square root of quantity x minus 4, and this whole thing needs to equal 3.2. So to solve for x, there's a few different ways we can handle this. One thing that we could do is transform that x minus 4 square rooted to an x minus 4 to the 1/2 power. Now you might be asking yourself, well, why would we do something like this? Of course, because we have this logarithm hanging out, that will actually take our exponent and move it into a coefficient. So we'll actually end up with something like 1/2 log base 5 of x minus 4 equals 3.2. Now, where are we going to go from here? Well, we need to get rid of this 1/2. So if we simply multiply both sides by 2, that will get rid of the 1/2 fraction. And over on the other side, it'll give us, instead of 3.2, of course, it'll just give us 6.4. No big deal. Now, at this stage, we need to talk about how to get rid of this log base 5. You've done this before in Algebra 2. It's really easy. Whatever the base is, just exponentiate it using that base. Of course, what that's going to do for us is it's going to essentially cancel out the log, and so we're left with x minus 4 equals 5 to the 6.4 power. For that, well, you're probably going to need a calculator, but I will tell you that that is 29,744.592. Of course, with that, we only have one step left. We need to add 4 to both sides, giving us a final answer of x equals 29,748.592. That looks like a crazy and ridiculous answer, but again, just like before, store it as x and feed it back through your original equation. See if it doesn't equal 3.2. That is one way of doing it. Is there another? I argue there are many others. Let's take a look at one more. What I'm going to do is I'm just going to rewrite my problem again. Log base 5 of the square root of quantity x minus 4 equals 3.2. This time, instead of turning the square root into a 1/2 power, I'm just going to go ahead and exponentiate right off the bat. And let's see what good that's going to do for us. Well, it is going to cancel out the logarithm, and it's going to leave us with the square root of quantity x minus 4. Over here I have 5 to the 3.2 power, and if you run that through your calculator, you'll see that that is 172.466 approximately. So at this stage, this is really easy. This is almost an Algebra 1 problem now. I just need to square both sides. That will get rid of this square root, and it'll give us x minus 4 equals 172.466 squared. Well, I'll tell you, that is 29,744.592. A very familiar number. We've seen that before. And so my last step, of course, just add 4. And if everything works out correctly, because we might not have done it the same way, but we did do the correct math, we should get the same answer that we got before. So there we go. X is 29,748.592. Again, a ridiculously large number, but plug it back in for x, and you'll see that this does in fact work. And so our math is correct. Now, before we move on to example C, we better take a look at how to differentiate expressions that have bases other than e, because if you look ahead, that's exactly what C is going to be asking for. So, without further ado, let's take a look at the box on the upper right corner of your notes. So you can see in this box, we're going to be talking about how to differentiate exponentials that do not have a base of e. In all 4 of these derivatives, a is going to represent some constant. And here's how this is going to work. I'm going to present these without proof. There's certainly a lot of proofs you can find if you research them. But if we're trying to differentiate some constant to the x power, the way we're going to do that is we're going to do the natural log of that constant multiplied by that constant to the x power. So you see, we're basically repeating our original problem, but multiplying it by the natural log of that base. Imagine what would happen if that base actually were e. We would get e to the x multiplied by the natural log of e, and you can see how, well, that would give us what we found out already in the last lesson. So there we go. But what if it's not just the derivative of a to the x? What if it's a to some function u? Well, that's actually not too much different. We're still going to do the natural log of the base. This time we're still going to do a to the u, but because of the chain rule, we better follow that with the derivative of u. So that's how it looks when we differentiate an exponential with any base. Of course, the base could be e, and you'd see we'd end up with a simplified version of this. So there we go. Let's take a look at one more thing if we want to differentiate a logarithm. And you can see in both of these cases, we do have a base of a once again. So if we want to differentiate log of x base a, that's also very easy. It's simply going to be 1 divided by the natural log of our base multiplied by x. So no big deal there. And this, you can probably suspect, is going to be something very, very similar. We're going to have 1 divided by the natural log of the base again, multiplied by the function u. But then, again, because of the chain rule, we do need to multiply this by du. I could write the du out here, but just for the sake of keeping it pretty sweet, I'm just going to throw the du on top. So there are our 4 derivatives that we need to be familiar with. Of course, if you're only going to look at 2 of these, my suggestion is you look at these 2 because, well, they can be simplified to deal with these 2 over here. So know these 2 formulas. You're going to need those repeatedly. And with that, let's go ahead and take a look at example C. Of course, it would be boring to just start off with a simple exponential derivative. So let's start off with this guy right here. Clearly, there are 2 parts to this function, and so we are going to have to use the product rule, but that shouldn't be a big deal. Let's go ahead and see how this looks. If I want to find the derivative of this, I'll have y prime. Maybe I want to start by differentiating the first part, the x. That will leave us with just 6 to the negative 2x here. And then if we want to differentiate the second part, so we'll keep the x, but the derivative of 6 to the negative 2x power, well, that's going to use what we just learned just a few seconds ago. So let's go ahead and start by doing the natural log of our base multiplied by our original function, 6 to the negative 2x. And then, of course, we better follow that up with the chain rule, the derivative of our exponent, which in this case is just negative 2. So if we put all this together, we'll have 6 to the negative 2x, and throw all this stuff together here. We'll have minus 2x multiplied by the natural log of 6, and then 6 to the negative 2x power. Now, of course, we could stop there, but that would be no fun. We do have a 6 to the negative 2x present in both terms, so we could go ahead and factor that out. We'll have 6 to the negative 2x multiplied by, well, out of this term we just have 1. And out of this term we'll have 2x multiplied by the natural log of 6. So that is how we apply the differentiation of an exponential. And you see, it's not really that big of a deal to do. You just have to have that formula memorized, and then it's relatively easy. So with that, let's take a look at one more example. This time we're going to differentiate a logarithm, and that, of course, will be fun and exciting. So here we go. We want to find the derivative of this logarithm function here, and this is a log base 10. So it's a pretty standard logarithm, but we still need to deal with this base and all that good stuff. So let's see what this one's going to look like. To do the derivative, we'll have y prime equals, and according to our formula, we'll have 1 divided by, remember, the natural log of the base, multiplied by our argument in our logarithm. So that's going to be x squared minus 1 over x. And then, because that is a function, we need to multiply that by the derivative of our argument. Derivative of this argument, well, of course, that's going to involve the quotient rule. So if we do that, we'll have the bottom multiplied by the derivative of the top minus the top times the derivative of the bottom. And of course, that will be all over the bottom squared. So if we go ahead and simplify that just a little bit, that'll bring us to x squared plus 1 all over x squared. There is our derivative of the argument. So let's go ahead and multiply what we have by that. This is the du part of the formula, and there it looks. So we can simplify this a little bit because this is quite hideous looking. Let's see here. The numerator, If I multiply those together, it's just 1 times x squared plus 1. So I'll keep my x squared plus 1 in the numerator. As far as the denominator goes, I still have my natural log of 10. But now I can multiply this big ugly thing by x squared. Of course, when I do that, the x right here will cancel out with one of these x's here. And what I'll be left with, let's see here, I'll have x squared minus 1 and that extra x that I have from there. So I could clean this up a little bit. It's really not necessary. But if this were a multiple choice part of a test, I doubt that this would be one of your choices. Probably the correct choice would look something more like this. X squared plus 1 on top. On the bottom, the natural log of 10 multiplied by, and really I'm just going to distribute this x. Easy enough. X cubed minus x. So that is the fully simplified version of our derivative, and that's probably what one of the choices would look like if this were a multiple choice part of the test. So you see how it works. That's how we differentiate a logarithm. And now that we know that, let's take a look at one more problem. A rather nasty looking problem, but a very common type of problem. We're going to differentiate using logarithms of this pretty nasty term. You can look ahead to example E and see what we're about to do, because here we go now. Y equals x to the x power. Very interesting function. It grows very, very quickly, but what we want to do is use logarithmic differentiation to find out how quickly it grows. Let's go ahead and find dy dx of this function. Of course, logarithmic differentiation, that's the big clue here, that we really can't use the differentiation rules that we learned earlier this lesson, because those only apply when we have y equals some constant to the x power. Here, we do not have a constant to the x power, we have x to the x power. But using logarithms, I think, will help us greatly in this endeavor. If we natural log both sides, look what's going to happen. We can now take this exponent and bring it down. So what we'll end up with is the natural log of y equals x multiplied by the natural log of x. And that, I think, we can probably deal with. Let's go ahead and differentiate this entire thing here relative to x. And if we do that, the natural log of y is simply going to be 1 over y multiplied by dy. Remember, that's the implicit differentiation. When we're differentiating a variable that's not x, we need to make sure that we use the chain rule, and there's our dy. Now, on the right side of this equation, we're going to use the product rule again. If we start with differentiating the first part, the x, what we'll end up with is simply the natural log of x. But now, if we differentiate the natural log part, we'll get x multiplied by 1 over x, which I think you can see how that one's going to simplify. So we're looking for dy. Let's go ahead and multiply both sides by y. And if we do that, that of course is going to cancel out this fraction, leaving us with just dy. Over here on the right side, we'll have y multiplied by the natural log of x plus 1. Of course, 1 because of this little thing going on here. So it looks like we're done. The derivative of y, we could say the derivative of y with respect to x, is equal to y multiplied by all this stuff. The problem here is that we don't want to leave any y's in the derivative. That can get kind of hairy. So, do we know what y equals? I'm going to argue that we do. And if you're not quite sure, go back to our original problem. Look, there's what y equals. And knowing that, we can go ahead and finish this problem up. dy dx is simply going to be x to the x power multiplied by the natural log of x plus 1. So I can feed any value of x I like into this, and this will tell me how quickly our original function is growing, or shrinking, whatever the case may be. So you see, it's a little bit of a process, but they did help us out by telling us to use logarithmic differentiation. That was the big clue, that the logarithm is the way we should start this thing, and from there it's just following the process on through. Pretty cool, huh? Well, before we move on to any more examples, we should now switch gears. Instead of talking about differentiation, now let's talk about integration. That's going to involve a couple new formulas, so let's go ahead and take a look at those before we move on. So here I'm going to introduce you to the integral for bases that are not e. And I'm not quite sure why this is in this lesson, but I also get the opportunity to present to you another definition of e. Of course, we talked about how e is the inverse of the natural log, but it actually has many, many definitions, and I get to present to you another one here. So let's go ahead and start with doing the integral for bases other than e. There's a couple different strategies I can take here. The first one is if I have some constant to the x power, one thing I can do is convert that so that it does have a base of e. The way I would do such a thing is I would simply write it as e to the power of the natural log of a multiplied by x. If you simplify that, you can see how that would give me a to the x power. So I could do this and then integrate that e, shindig going on here. That's one way to do it. Not the most common way, but one way nonetheless. Perhaps a more useful way would be to integrate it directly. So if I have the integral of some constant to the power of x, the way that I would evaluate that integral, it would simply be 1 over the natural log of the base, which I'm getting used to by now, multiplied by a to the x power. And of course, don't forget your plus c. Now, in these notes, for whatever reason, I'm not presenting to you the integral of a to the u du, but if you've come this far in this course, I'm sure you can figure out what the integral of au du would look like. So I'm not going to present it here. You can figure that out yourself. Well, with that, let's take a look at the limit definition of e. E might have been presented to you in the past, perhaps in Algebra 2 or pre-calculus, as a compounded growth kind of constant. And compounded growth does look like this. We take 1 plus 1 over x repeatedly, and that's what this x power means, repeatedly. And if we do that as the limit of x approaches infinity, you see that we're growing very, 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 very little bit each time. Of course, the limit of 1 over x is 0. So it's 1 plus this very infinitesimal amount, but we do it a whole lot as x approaches infinity. And if we do that, what we'll end up with is that constant e. Of course, this could be rewritten as simply x plus 1 over x. Either way, the limit as x approaches infinity of this will give us e. Try doing it in your calculator if you have that ability. Do the limit of this function, x plus 1 all over x to the x power as x approaches infinity. I bet you're going to get something that harkens very closely to the value of e. In fact, it should be exact, so there you go. But now that we've talked about the integral of bases other than e, that will allow us to proceed with example f. So let's go ahead and move on to that now. So although I didn't show you how to integrate a constant to some function in the box that we just did, I assume that you're able to do that on your own. Of course, to do this problem, we are going to need a u du substitution. After all, it's one of my favorite things to do anyway. So if I want to do this, I'm going to let u represent the exponent. So that will be quantity 3 minus x squared, no problem. Of course, then du will simply be the derivative of that, which is going to be 2 times the quantity 3 minus x to the first power. Now, of course, I do need the chain rule here. Never forget about the chain rule. The differentiation of this 3 minus x is simply negative 1. So I'll just go ahead and throw a negative out front and include my dx. Now that I've done that, I can go ahead and turn this integration problem into terms of u and du. So let's see how that works. Let's see here. I'll have the integral. I do have, well, this will be 7 to the u, but actually I don't have du. du is not there. But to make du happen should not be a big deal. All I'm really missing is this negative 2. So I will introduce the negative 2 there. I'll have my quantity 3 minus x, 7 to the 3 minus x quantity squared dx. And to balance that negative 2 that I just kind of introduced, I'll put a negative half on the outside. And now I can go ahead and rewrite this integral in terms of u. This will be 7 to the u power followed by du. Notice that I have all my pieces in place for du. The negative 2, the quantity 3 minus x, and the dx. So this is good to go. Now that I have this integral, now I can go back to the box and integrate this, hopefully with no problem. I'll have negative 1/2, and then when I integrate this 7 to the u, that'll of course give me 1 over the natural log of 7 multiplied by 7 to the u plus c. And now it's just a matter of unsubstituting my u's, and what that'll do is give me the negative 1/2. I'll have 1 over the natural log of 7 multiplied by 7 to the 3 minus x quantity squared. Don't forget your plus c. Now if I want to, I can put all of this together. I can put this together even more than it already is. If I take this 7 to the ridiculous power and put it in the numerator, along with this negative 1, what I should get in the numerator is negative 7 to the 3 minus x quantity squared power. In the denominator, I'll have 2 natural log of 7, and 2 natural log of 7, of course, I can turn that, if I want to, into the natural log of 49. So there is my final answer. Again, if this were a multiple choice problem, that right there would probably be one of the choices. Don't forget that 2 natural log of 7, I can take that 2 and move it up as an exponent, and that's where I get my 49. So now that we've experienced the integral of a constant to some power, let's go ahead and move on to our last example of this lesson, where once again we'll be working with slope fields and differential equations. Good times! Let's go ahead and tackle it now. So here in our last example, we're going to work with a slope field and differential equation as promised. Interestingly enough, this particular problem you would have been able to do back in the last lesson, in lesson 5.4. However, it shows up here in 5.5, so we'll handle it as they come. You see here that I am given a slope field with lots of little pieces of slope, and I am given a point, and you see it there in blue. That's the point pi comma 2. Now the directions state to sketch 2 solutions on this slope field, one of which passes through that point. So I'll go ahead and do it for you. And what we want to do now is find the solution to this differential equation, and furthermore to find the particular solution that passes through that point pi comma 2. So the way we're going to do this is we'll first split up our dy and dx, and we'll do that simply by multiplying by dx on both sides. And if we do that, we should get something along these lines here. Now, of course, what we want to do is integrate this to find our solution. So if we go ahead and integrate on both sides, it'll look something like this. And this will need a u du substitution. I'm going to posit that we use the exponent as our u. So u will be sine x, and du will then, of course, be cosine x dx. Unfortunately, I don't even need to mess with this integral. Everything is laid out perfectly for me. So the left side of this integral will simply turn into a y, and the right side of this integral will now be written as eu du. You see that the exponent is u, and the remainder of this is actually du as it sits. So that's pretty nice. Now we know how to integrate e to the u du. That's just going to give us e to the u plus c. Or if we want to unsubstitute, this will simply be y equals e to the sine of x plus c. That is our general solution to this differential equation. If we want the particular solution passing through the point pi comma 2, let's just do a little bit of work. Y will be 2 and x will be pi. And all we need to do then is just solve for c. Well, let me go ahead and work this out a little bit nicer. What I'll end up with is 2 equals e to the sine of pi is actually just 0, and then plus c. And if you work that out a little bit, you'll find that c must equal 1 then. So our particular solution to this problem is going to simply say y equals e to the sine of x plus 1. And that is the graph that we have going on right here, the one that passes through the point. And so everything came up roses. Pretty sweet. Alright, so here in lesson 5.5, we haven't covered a whole lot, but we have seen some very, very important formulas. Before we got to those formulas, we started by simply doing some practice with exponents and logarithms, kind of reminding you of what you did back in your Algebra 2 days. After a little bit of practice, we jumped straight in to looking at the derivative of exponentials and logarithms, in fact. Of course, if the exponential has a base of e, we already knew how to handle that. But now we know how to handle the derivatives of exponentials that have a base other than e. That's very important. Of course, this is more of a general case. If you plugged e in as your constant, everything would work out just like it did before. After we did a little bit of practice differentiating exponentials and logarithms, we then went ahead and learned how to integrate exponentials. Now, as far as integrating logarithms, don't worry about that right now. We'll get to that later. But we do now know how to integrate exponentials when the base is something other than e. We even looked at a problem where we did a logarithmic derivative. Jumping back to the derivative, so that was a little bit of a mess, but it all worked out fine in the end. And we finished this lesson by looking at one more example of slope fields and differential equations. Are you starting to get the feeling like these are kind of important? I would argue they're extremely important. They will be tested on for the rest of the course, and even beyond BC calculus, you will see these slope fields and differential equations in higher levels of calculus and mathematics. So, with all that being done, this was a very fun and exciting lesson. Remember those formulas. Commit those to memory. You're going to need those. And good luck on this assignment.